Here in this question, we have a thin conducting ring, and this thin conducting ring is ruptured when it's given a charge Q. So the question says that when you have another thin conducting ring, which has a radius n times of this ring, and its tensile strength is k times that of the former ring, then what's the maximum charge which can be given to this ring so that it doesn't rupture? Okay, so we'll have to first think about why this ring ruptures when we give a charge Q based on it. So let me consider that case. So you have a ring having a charge Q. This ring has a radius, let's say R, and the tensile strength of this material. Let me assume the tensile strength of this material to be equal to sigma, right? Okay, so the idea behind this question would be to think about why this ring ruptures when a charge is being given to it, right? So let me, and that will be much more easily understandable if we consider a small portion of this ring. So let me consider a small portion of this ring. Let me consider a portion of the ring which subtends a small angle d theta at the center. Okay, so now when I draw a free body diagram for this d theta, right? What are the forces acting on this? We realize that there are forces due to the other portions of the ring, right? Since your ring is entirely charged, you will have a force acting on this portion due to the other portion of the ring, right? Now I can express this force due to the other portion of the ring on this portion in terms of the field which is created by the other portion of the ring on this part. So let the field due to the other portion of the ring at this part be equal to E. So then your force acting on this will be equal to dq into E, where dq is the charge which this has. Okay, so now what will this value of E be equal to? So here deriving the exact expression for what the electric field is not necessary, and it might also be a slightly complicated process. So the idea here to go about this is we only have to think in terms of proportionality, right? So we'll say that every charge which is present over here, will exert a field on this ring at this point. So it is the sum of field due to all the point charges. So the idea here is to say that your electric field due to the other portion of the ring, your electric field of the remaining portion of the ring at that point, will say is proportional to the charge given to the ring divided by the radius of the ring, right? Because everything will be in terms of, dq divided by distance squared, dq divided by distance squared. And the distance is essentially proportional to r squared. So I can write that in terms of a proportionality constant. I can say that this electric field at this point is equal to some beta into q by r squared. If that's the case, then what will be your force acting on this? Your force acting on this small portion then will be equal to, so writing down that force expression, that force value will be equal to, dq will be equal to q by 2 pi into d theta, and then into beta into q by r squared, where q is the charge which is being given to this ring, right? So this force expression turns out to be q squared beta by 2 pi r squared into d theta. So we have a rough expression for what will be the force exerted by the remaining portion of the ring on this portion of the ring, right? Now, why is this not moving away? Why is this portion not getting repelled? So the force which is responsible for preventing it from getting repelled is your tension force over here. And how is the tension force acting? Your tension force will be acting in this way. Your tension force will be acting along the tangent. And this tension force is what we're relating it to tensile strength, right? Okay, so let's get a relation between this force and tension over here, between the repulsive force and tension. So this, let me draw a chord. We know this angle is d theta, so half of this angle will be equal to d theta by 2. So this angle will be d theta by 2, which means this angle will also be equal to d theta by 2. So your component of tension acting this way will be equal to t sine of d theta by 2. The other component of tension also will be acting over here, and that will also be equal to t sine of d theta by 2. Your horizontal components of tension get cancelled out in this case, right? So it's the vertical components of tension which is acting against this force and preventing this from going away, preventing this from getting repelled. So then writing the equilibrium expression, your equilibrium expression then will become equal to 2t sine of d theta by 2 is equal to q squared by 2 pi r squared into your proportionality constant beta into d theta, right? Since your angle is a small angle which you're considering over here, we can write sine of a small angle to be equal to theta itself. So this expression then becomes equal to t into d theta is equal to q squared by 2 pi r squared into beta into d theta. D theta gets cancelled. So this is your expression for tension. Your tension is equal to q squared by 2 pi r squared into beta, right? And this is the tension, like this is the amount of maximum tension this this ring can handle, right? Because it's mentioned that when you give a charge q, this ring will rupture. So this is the maximum tension it can handle. And now let's look at the next. Actually, it's given in terms of tensile strength. Tensile strength, to be precise, is tension divided by area. But area of cross section in this case and the previous case is the same only. So we'll relate it to tension itself. So this is what we'll say is the maximum tension this material can handle, right? So then how do I get the expression for charge then? So we can say q squared is equal to 2 pi r squared into t by beta, or q is equal to under root of 2 pi r squared into t by beta. So this is the maximum. So we got a random, not a random, but a rough expression for what is the maximum charge your ring can handle when you are placing a charge q1. I mean, what is the maximum charge q which this ring can handle? And that expression we have got it in terms of the maximum tension it can handle and in terms of the radius as well. Okay, so now we are considering a new ring, and this new ring has n times the radius of the former thing, and it has k times the tensile strength of the former rings, right? So what is the maximum charge which I can place on it right now? So if you notice, every other step over here will be similar. We'll be writing a similar kind of expression. So we'll end up with almost a similar case. The only thing over here is your radius now increases by n times, and your tension now increases by k times. So the maximum new charge which your ring can handle will also, if I take a proportionality thing right now, your maximum charge will also now become equal to root of n squared into k times of the previous charge which it can handle. So the maximum charge this ring can handle right now will be equal to n root k into q. So this will be a solution for this question, right? Hopefully this made sense. See you guys in the next question.